get started. Our next speaker is Devarsh from TI, talking about handing off display between the bootloader and kernel and all the complexities there. So take it away.
Good afternoon, everyone. So I'm Devarsh, and today I'm going to speak regarding how we can achieve smooth transition of display context across the bootloader stages while kernel is booting and right up to when the display server comes up. And along with me, Tomi helped with the upstreaming and the review part. So at TI, we are involved with different open source projects, and I mainly focus on the media side of things, like open source media frameworks and kernel subsystems related to audio video. So this is the outline of the presentation. So we'll go with the understanding the problem, like what is the problem here, what are different subparts of the problem, then what are the use cases that we want to support. Then we'll see like what potential solutions are and how much is already present in the upstream and what is in the pipeline. Then we'll see how this can scale to different subsystems also, like how we can generalize the solution. Then we'll see what are the current status of this. So here's the use case. So let's say we set up a boot logo in the first stage bootloader. Then what we see is like we shift to the next stage, let's say from the SPL to the U-boot. Then the logo gets corrupted. Then again kernel, at the start of the kernel boot up, it again gets corrupted or the memory gets reset. Then you have your display driver getting loaded. So in this case also, like your memory will get reset and you will see a blank screen. Then for a brief period, FBD emulation will come up. So your service like psplash or something will try to display some animation, but again it would stay for a very short time and will then transfer to the Western. So there are multiple times where the display context is lost and there is a flicker that the user sees. So if you have to understand the root cause of the issue there, then there are only mainly two reasons. One is the memory. So on each transition, the memory is getting reset and the next stage doesn't know that the initial or the previous stage had set up a bootloader there. So the memory context is get lost, and also there is new memory that is getting allocated for the same purpose. So there is a memory loss also. And the second thing is like each stage there is again a refresh of the IP in the pipeline. So every on the each stage the video IPs are getting reset, the power and clock domains get toggled, and on the each probe of the new driver on the transition will get a soft reset. So let's say if you have a display controller, then you have a PWM to control the backlight, then you have I2C controlling the display, or a DSI to DP bridge, or LVDS to HDMI. So all these IPs in the pipeline. So even if they are initialized in the bootloader, kernel will reinitialize it and it will reset the display context. So mainly we are targeting 3 use cases to support. So number one use case is like you start with a boot logo and then you want to display some boot animation in between before main GUI comes up. So second use case would be like you start with a boot logo and you want to preserve that boot logo till the your graphical user interface comes up. And the third use case would be like you want to start with the boot animation itself and you want to continue the boot animation until the OS boots up. And all these transitions we want to achieve with a minimal footprint, without any additional boot time delays, and without any flicker. So we'll take the example TI's K3 DSS and oldie as an interface because it's a simple one. and there is already some support being pushed for the same. So this is the first use case that we want to support. So we have the boot logo set up by the bootloader. Then in between we want to show some animation while the kernel is booting up using a psplash service. And then when the display server comes up, until then the animation should be displayed. And after the Western comes up, we want to show the Western context. So to achieve the smooth transition across the bootloader stages, we already have added a framework support for this. So what you can do is, like in your SPL stage, you can set the blob list structure, and what the framework will do is, like, it will collect the metadata for the frame buffer that is set up by the bootloader, create a handoff structure, and handoff structure will contain the frame buffer address, frame buffer size, frame buffer coordinates, and then it will pass this to the next stage. So using this blob list, your next stage bootloader, that is a U-boot proper, it will collect this metadata, and it will pass this metadata. And that is one problem. So we are okay with the memory part of it, but again there is a power and clock domains that need to be kept on when we are transitioning. So for that, there is a flag called DM flag leave PD on, which you can set in your U-boot driver. And with this, even if the remove method of the driver model gets called, your power domain won't go off. So for more details, there's already talk, you can refer that as well. So now we have smooth transition across the bootloader stages, but when the kernel starts booting, we again see corruption in the screen, and we want to show some animation here instead of this corruption. So again, like across each transition, the requirement is, like, you have to take care of the memory, you have to preserve the memory state, and you have to preserve the IP state. So for preserving the memory, what you can do is, like, you can reserve the frame buffer memory using the reserved memory node in the kernel device tree. And for preserving the IP state and for supporting the animation, you can use something called simple frame buffer. So simple frame buffer is like an early frame buffer device. So even if, let's say, your display controller is not probed and you want to display something on the screen while the kernel is boot up, then you can enable this simple frame buffer. Using this kconfig, it will create a early frame buffer device node, and your psplash or any other application can use that to show some animation. So with this, your animation service will be okay, but you also need to preserve the IP states. So you can specify power and clock domains in the simple FB node. We'll see more details in the further slide. So we want to automate this, right? We don't want to hard code frame buffer address in the device tree. I'm sure maintainers won't like that. So what you can do is, like, you can define a static node for simple frame buffer and keep the status as disabled, and you link it to your display driver and specify the power and clock domains. And in the U-boot, you can call this API, which will dynamically update the frame buffer node with the frame buffer address and size and switch the status to enabled. And it will also create a reserved frame buffer memory node with the address that was set by the bootloader. And if you don't want to use the simple frame buffer, then you can directly call this API to just reserve the frame buffer. So with this, we are able to achieve smooth transition while the kernel is starting, and also able to display the animation while the kernel is booting up. Now let's understand how simple frame buffer is helping preserve the IP state. We specified the power domains, clock domains in the device tree for the simple frame buffer, but why exactly this was required? So if you see the platform probe code on how kernel probes each driver. So what it does is like it will pass a device tree and call the driver probe, and while calling the probe of that display driver or any other driver, it will try to attach to the PM domain. So this will power on the it will take a reference to the power domain of the corresponding driver. Then it will call the probe of the driver. Now if your probe fails, then it will detach the PM domain. So if, let's say, your display driver is getting probed, and there are dependencies of your display driver with some other drivers such as bridge driver or any other PWM or any other drivers which are not yet probed. So in this case, there will be a probe deferral and this will fail. Now it will call this PM domain detach, and when this, your power domain will go off. So what essentially is happening is like JanPD has no knowledge of what power domains bootloader has enabled it. And when this probe deferral happens, there is a power domain off call that gets triggered for your display driver. And with this, you see a flicker. So if you add the power domain information in the simple frame buffer node, it kinds of adds an extra reference to your power and clock domains, and it helps avoid this deferral problem of toggling the power, because there is an extra reference to the power domain, so framework doesn't power off your IP even if there is a deferral happening. So what about simple DRM? So let's say instead of simple FB, you want to use the simple DRM. So simple DRM can also be used similar to simple FB. You can preserve clock and power domains, and it will create a /dev DRI card node instead of RDFB. And let's say you have some animation service that relies on the DRM card, then this simple DRM will be useful for that. But one catch with simple DRM is that let's say you want to use the FBDev emulation with the simple DRM, then the FBDev emulation uses a separate buffer. And when there is a application that is trying to use the FBX that is created by the simple DRM, there is usually a new buffer that gets attached to the FBDev, and there is a mode set. It will clear up the screen. So you need some custom logic to copy the bootloader buffer to your FBDev emulation buffer to avoid this flicker. And so the disadvantage would be like there would be higher memory footprint as compared to simple FP. So now let's see what happens when your display driver gets probed. So we have achieved clear transition until simple FB, but when the display controller gets probed, we again see a blank screen. So this is because the display driver will again reset the display. It doesn't know that bootloader has already initialized the display, so it will reset the display on the probe. So to avoid that, what we do is like we detect first on the probe that if the display is already on. So we check some registers and see if the display is already idle or in the running state. Then we check what all CRTCs are getting used, again where a register reads, and we mark using a flag mask like what all CRTCs are enabled, and we take a reference to the required clocks for those CRTCs. And then we take an extra PM runtime reference so that the framework doesn't disable the power and clock domains. So until the new mode set happens, let's say until your Western comes up, we won't reset the display. As soon as there is a new mode set happening, new atomic commit happening, only at that point we'll reinitialize the display. So there are already patches posted for the same. So now we have a smooth transition until the display driver gets probed. But again, when the FBDev emulation comes up, we again see a blank screen. So as I mentioned, FBD emulation, it uses a separate buffer for the atomic commit. So it doesn't have any knowledge of the bootloader buffer. So what we do is we copy the bootloader buffer contents to the FBD buffer during the FBD driver probe. So this way, FBD emulation driver does a mode set with the bootloader buffer itself. So with this, we are able to preserve the bootloader buffer contents, and we are able to have a smooth transition. And alternatively, if the FBD emulation is not required by the system or your product, then you can just disable the FBD emulation also. So with this, we are able to achieve smooth transition until the FBD emulation and then to the display server. Now let's say we don't want to display any boot animation. We want to just display the boot logo that was set at the start of the bootloader all the way until your Western comes up. So there is no animation requirement. And also we don't want to use the simple FB. So what is a more generic way to support this? So again, if you remember the power domain problem that we discussed, like on the probe referral, the GenPD framework powers of the driver that it sees as unused. So if we have to avoid that problem, we have to inform the GenPD framework what were all the bootloader enabled drivers and what all drivers that need to be stay on. So for this, there have been some patches posted. So the basic idea is like the GenPD provider driver, it will parse the power domains that are available in the device tree, and it will use an API to talk with the firmware to see what all domains are already on. And it will pass on this information to the GenPD framework, and GenPD framework will set a flag called stay on for all these peripherals. So based on this, what will happen is there is an extra reference for all these power domains by the GenPD core. So these power domains won't get powered off until something called sync state happens. So when all the power domain consumer drivers are probed successfully, then something called sync state API will get called by the GenPD framework. So what it will do is like it will release the extra reference for the bootloader enabled peripherals that we took at the initial stage. So it will reset the flag and it will release the extra reference. And if you don't want to wait until the sync state happens, then on the boot up, you can simply pass a flag, pass a Boolean variable to set the state as synced, and this will trigger the sync state call manually. So just to summarize, there are like 3 steps here. One is your GenPD provider driver has to parse all the power domains that are already active and set by the bootloader. Then the framework support is there, which will keep those bootloader enabled peripherals power domains status as active. And third is this sync state, which will happen when all the power domain drivers have probed successfully, and it will release the extra reference. So after this, if your driver is not getting used, it will get runtime suspended. So what are the challenges with GenPD sync state? So one, or more precisely this solution. So first is like the GenPD provider driver, it needs to query each and every peripheral, whether it is on or whether it is off. And this kind of adds an extra delay to the boot time. And these power domains are generally managed by a separate entity. So normally there is an MCU that is in control of the power management stuff for all the peripherals. So we have to query that firmware via IPC and get the status of each IP, so it can add to the boot time up to level of several milliseconds. So what we thought of is like we can get a combined status of all the power domains using a new uh, custom API for talking with the firmware. And if you are using SCMI, then maybe SCMI can support something for parsing all the power domains in one IPC call. The other solution is like we as user can provide all the peripherals of interest, like on the device tree, which all peripherals are bootloader enabled. Then the GenPD provider driver will only check the status of those peripherals and keep them as stayed on. So if you see it in a different way, it's actually a generic problem. It's not just related to display. Let's say uh, your device is starting and you want to play some audio tone along with the boot animation. So your audio is started by the bootloader, and you don't want to block the boot up process when your audio is playing, right? So you want to play the audio tone, and your boot up process should happen in parallel. So your kernel will boot up, your sound driver will come up, Western will come up. So till then, if there is an audio tone that is playing, and if your boot up time is like 2 seconds or something, then this audio should continue to play. So here also this GenPD sync state solution can help because it helps preserve the power clock and the IP states. And it also helps with the boot time optimizations, as we are skipping initialization of already initialized IPs that were set by the bootloader. So until your kernel boots up and until there is a different setting required for your peripheral, you can preserve the initialization state what your bootloader has set and continue to directly use the IPs instead of reinitializing them. Now goal number 3, let's say we want to support animation right from the start. So your remote core is will be used because unfortunately U-boot doesn't support interrupts, so we cannot use U-boot to display animation. So you have something like your remote core or MCU that will set up the display and set up animation, and we want to continue to use that MCU controlled display application to continue rendering the animation until Western comes up. So for this, we need some sort of inter-processor communication between the RTOS and Linux. So MCUs will be booting up early in the system. They will render the animation and will preserve the memory area that is being used by the MCU using the reserved memory region, and will disable the FBDIV emulation. But we don't have any handoff, like Linux doesn't know, RTOS doesn't know when the Linux has already booted up, right? So we need some handshake between the RTOS and Linux to tell that Linux has booted properly and it wants to take back the ownership of display from the RTOS. So what we need is some sort of IPC. So what we are thinking is like when the Linux boots up, it will kick a mailbox which will generate an interrupt to the remote core, and after then the remote core will clean up the display, relinquish the control of display, and send an acknowledgement back to Linux, and Linux will receive an interrupt, and then the Linux will take control of display and pass it on the Western. So there's no standard API for this, but we can use something custom like inside our driver to have this smooth handoff. So what are the open challenges or gaps that are not yet upstream, or what we are trying to see? So number one is like we are basically reserving the bootloader memory using this reserved memory node, but this memory is kind of getting wasted because nobody is freeing this memory. So even if your simple FB gets over and your kernel is fully booted, your display driver is running using separate buffers, this memory is still not available to Linux. So we don't have a mechanism to relinquish this memory back to the system. Second problem we see is like especially with systems which don't have GPU, we see a small flicker when the Western starts. So haven't looked up at the Western code, but what we assume is like Western is creating a zeroed buffer and it does a mode set before a GPU has fully rendered that buffer, or it's doing some atomic mode test check before it's doing the actual mode set. But we see some brief flicker when the Western starts. The third problem is the copy that needs to be done with the FBDIV emulation, because there is no direct way we can map the bootloader buffer with the DRM structure which this FBDIV emulation uses. So we have to do a copy at the start of the FBDIV emulation probe. So it's kind of wacky and doesn't look good. So we need to find a way to have a generic solution for this. Fourth is the GenPD sync state API. So this kind of is getting called very late in the cycle because it is waiting for all the drivers to get probed and then only it calls the sync state. So this kind of uses the power, keeps the power domains of all the IPs as on, even if they are not getting used until the sync state happens. So what we want here is some atomicity, like as soon as your display driver gets probed, you want a sync state, and if your display is not getting used anymore, it should runtime suspend. So what the idea here is to have per device sync state calls so that we don't have to wait for all the drivers to get probed and do a common sync state. Instead of that, we'll have per device and per driver sync state calls, so that as soon as the IP driver gets probed and if it is unused, then it will runtime suspend the device and there is a power saving there. So there is already some discussion happening to extend the firmware labeling API to support this. And last is like there is no standard API for IPC between Linux and remote core for the display. So right now we are planning to use some custom API to support this handoff. Yeah, so I would like to thank Texas Instruments, Ideas on Board, and Embedded Recipes, and the BayLibre to giving this opportunity. And I'm open to questions. Thank you.
Almost. So, as far as I understood, you have kind of custom solution for single or narrow amount of boards and which has specific hardware designs. For example, MCU, which starts first, and then specific SoC, and then some other frame buffer. Do you plan to do actually anything generic? Because not all platforms, even device tree platforms, for example.
So MCUs, we generally want to support as an early starting point is because they boot faster and they are having that interrupt support and framework support like LVGL to display animation, which U-boot doesn't have. And second problem, we cannot have an RTOS only display because RTOS doesn't have the GPU drivers. So at some point we have to transfer back to the Linux. So that's why we need this transition.
Yeah, but my question was about different platforms. Not all of them have even that kind of MCU to begin with.
Yeah, so yeah, it is not for all platforms, but some platforms you want to support. So what is your question, like in the other platforms you want some other use case, or?
The question is if you are going to support something more generic like a protocol and you don't care if it's MCU behind or any other BIOS. Or
Yeah. So for this appears to be a custom use case, so we don't care about protocol, but there are other use cases where you want to control the display fully via the remote core. For example, the Raspberry Pi FKMS driver is there. It controls the display via MCU, and there's a rapid driver on the Linux side. So for those kind of use cases where you want to drive the display via remote core due to some reasons, and but you still want to use GPU to render the buffer. So for this, that you need to have a rapid driver in the Linux or have some IPC mechanism to talk with the remote core. So maybe for those kind of use cases, like similar to your sound open framework, you may require some protocol. But yeah, it's early stage, and if we are the only one, then we'll probably start with something custom and see how it goes from there.
And also, second question is about different resolution. For example, firmware or bootloader could initialize display in one resolution, and then DRM driver, when it gets over, it could
Yeah, so for this particular use case, we are not trusting what RTOS has said. We'll reset the display and take the ownership.
Yeah, and you get flicker.
Yeah. We'll get the flicker only when the Western starts, but yeah.
Hi, thanks for your talk. So we had a similar problem with the sync state thing, but we solved it by keeping a flag in the kernel if we have, let me think again. So the problem for us was that we had a reference in the simple frame buffer node, and we had the power domain, but the power domain was still being shut down because the device hadn't probed yet. So what we did is that we do not shut down any power domains until the time where the kernel would power down unused power domains. You know, so after the system has booted, it powers down unused power domains.
Yeah.
And wouldn't that work for you too? Do you really need all that sync state synchronization? Wouldn't it be enough that you just don't shut down any power domains until the time where you would shut down unused power domains? And I am also wondering how that works in conjunction with modules. So if you have a module for a device, but you never load that module, will you never power off anything?
Yeah, so there are a couple of things related to this. One is like, if we go by what you propose, right? If there is a probe deferral happening, then in that case, the power domain will get off, even if before your driver is probed successfully. So in that case, we see a flicker. And second is like we are supporting something called as late initialization in each of the video related drivers. So we are basically delaying the reset of each of the video drivers. We're detecting what all the IPs are already on, which are display related. And in those drivers, we are keeping the power and clock domains on, and we are avoiding the reset for those. So as soon as your probe will get called, you will reset the display, right? So
no, because you will not. You disable the shutdown of all power domains until the time where you would garbage collect unused power domains.
How did you disable all the?
You would need to add a flag to the kernel.
Okay.
But you wouldn't.
I mean, the idea there is what sync state is meant to do, but it's since sync state exists for other subsystems, like for clocks and regulators and things like that, applying it to the power domains is kind of more, because you're talking about modifying the power domain driver to add a flag. That's essentially what sync state is doing. It's just slightly more generalized. But the idea is exactly the same.
But what are the implications for modules? If I have a module and it's never loaded, do you still?
So then we have the alternate mechanisms, like in your boot script, you can call the sync state manually by setting the sysfs entry, or there will be a timeout also. So after a setting timeout, sync state will get called for all the domains.
Okay, thank you.
it is more generic question, probably not only to you, but everyone in this room. This is not only graphic or sound problems. So I have customers which requesting something like, can we keep the network running? Because they have devices which run in the field and making net boot and so as fast as possible. So we need some kind of hunt of protocols, whatever, between bootloader and kernels, and we can synchronize things and say, okay, this PHY should be kept on and in its initialization state, but at the same time, we should be able to control it and reset if things going wrong completely. So kind of recovery fallback. And still, I don't know what is the best way to do it, and not just hacky way in the project, but upstream way.
Yeah, so if you have to like generalize it for all the drivers, right, then we have to support something called as late initialization or preserve the initialization state of the IPs. So right now we are adding this for the each driver separately to detect if it was already bootloader powered on and avoid the reset. But instead of that, if there's a late init call or some generic API to tell or trust that it's already powered on by bootloader, then maybe that could be generalized for each driver.
Okay, thank you. Thanks, everybody.
Thank you.